One technology in the spotlight is the IoT, or Internet of Things. It makes it possible to collect information via the network from devices equipped with sensors and communication facilities. Some researchers predict that the number of such networked sensor devices will reach 1 trillion, ushering in the trillion sensor universe era. Now we are facing a problem of how to maintain such a huge number of devices. Since the power consumed to process sensor data cannot be estimated accurately, it has not been possible to avoid sudden battery depletion. For this reason, it has been necessary to replace batteries well before they become fully depleted. Moreover, unexpected abnormalities caused by failures can stop sensor networking systems from functioning. To realize the trillion sensor universe era, we need a reliable and innovative sensor networking system that is free from sudden battery depletion and that works autonomously and reliably even when the unexpected happens. This video will present a data-driven processor, the only processor that makes it possible to realize such innovative sensor networking systems. The video will also show its applications. A data-driven processor operates on a non-traditional principle. While processing one item of data, it can accept another and process both in parallel. Hence, the data-driven processor can concurrently process both contiguous data, such as video data, and non-contiguous data, such as sound samples, which occur less frequently. Moreover, unlike conventional processors, the data-driven processor has data flow architecture. Traditional processors must store every item of data in memory before processing it. In contrast, in a data-driven processor, data is fed directly into the processor. Consequently, this type of processor does not require as much power or time to write data into memory and to read it out from memory. This is why data-driven processors are ideal for stream processing. These features make it easy to provide wireless sensor network systems with advanced sensing capabilities, even the ability to deal with images from cameras, which is difficult for conventional processors. One of the promising applications of such a wireless sensor network system that includes cameras is monitoring the wear and aging of bridges, expressways, and tunnels. Also, it is possible to detect illegal activities. Since monitoring by humans is expensive, the key is how to replace human senses, such as eyesight and hearing, with sensors. For example, right after someone has broken into a site, the suspect's activities can be recorded and later presented. This video shows how, in the event of an earthquake, a sensor system takes and transmits a photo of the monitored object. This is a sensor node prototype, a data-driven processor, an acceleration sensor to detect tremors, a camera to take a photo, and a wireless communication unit are mounted on it. Just after detection of a tremor, each node takes a photo. And then the photo is broadcast to nearby nodes immediately. The broadcast photo is finally transferred to a monitoring center, which analyzes the photo and decides whether to request the dispatch of personnel. Since the data-driven processor is based on stream processing, it requires no special control, so it consumes the minimum power required for processing. For this reason, the current consumed by the data-driven processor is proportional to the processing load. We can see this proportional relation from plots of the current consumption on the vertical axis and the number of tremors over a given period on the horizontal axis. This proportional relation makes it possible to predict the total amount of current consumed for an estimated number of events, allowing the precise estimation of the operating life of a given battery. The predictability of the total current consumption also makes it possible to realize the novel function of autonomously detecting any abnormality. For example, sensor failures may generate an unexpectedly large number of events. Erroneous reporting of an unexpectedly large number of events results in power being wasted, not only for event processing but also in the neighboring nodes that receive the unnecessarily broadcast photos. However, conventional processors cannot detect abnormalities in real time. In contrast, the data-driven processor can detect an abnormality when current consumption deviates from the assumed range. In addition, the unnecessary broadcasting of photos increases the current consumed by the neighboring nodes, so nodes can monitor each other by observing the current consumption of individual nodes. This mutual surveillance makes it possible to detect and isolate abnormal nodes, a unique and original feature for keeping the network system functional and ready to operate at any time. On this display screen of the sensor node prototype, nodes are connected by dotted lines, which indicate the radio reachable range. Broadcast photos are propagated through the network to adjacent nodes in bucket brigade fashion. For instance, a photo broadcast by Node 2 is received by Node 5, and then Node 5 rebroadcasts the photo to other nodes. Repeated rebroadcasting of photos relays them onwards. A photo may be received by more than one node, and the same photo may be relayed by different nodes. When a node recognizes repeat broadcasts of a photo that it has already received, it discards all subsequent repetitions, thereby preventing rebroadcasting of the same photos by the same node. This is how wireless networking operates. When the number of neighboring nodes increases in wireless networking, broadcast data may be lost due to radio interference. We have introduced an original scheme in which nodes stop relaying data when radio interference is excessive. This scheme can ensure reliable delivery of data, such as photos, throughout the network. In addition, reduction in unnecessary relaying lowers power consumption. The autonomous detection of abnormalities makes it possible to localize the adverse effects of node failures, such as the broadcasting of unwanted data. Specifically, a node that has detected its own abnormalities stops broadcasting data. Even in the event that abnormal nodes cannot stop broadcasting, the excessive current consumption in neighboring nodes, for example from receiving too many photos, exceeds the assumed range and can trigger the recognition of a problem. Upon detecting an abnormality, nodes discard the photos received from the abnormal node, so the adverse effects can be localized to remain within one hop radio range of the abnormal node. Photos from an abnormal node never propagate to nodes further than one hop, and thus the processing load of remote nodes does not increase. This processor can provide advanced functions, such as a sensor hub. Up to now, it has been necessary to prolong the power-off state or sleep time of an application processor in order to economize on power consumption. A sensor hub is additionally required to collect and assemble infrequently sent data in order to extend sleep time. In contrast, the data-driven processor operates only when it has data to process. Thus, it does not require sleep time. Furthermore, the data-driven processor consists of small working units called pipeline stages. Any pipeline stage that has no data to process goes to sleep, so the sensor hub's function is no longer needed. Let us show you another application. Autonomous detection of abnormalities can also be useful for detecting cyber attacks, such as a denial of service attack, which disrupt network services. When a network device is executing a malicious program, its processing load increases, and its current consumption exceeds the normal range. This is one way that such an attack can be detected. As in the case of failures of sensor nodes, the adverse effects of detected attacks can be localized. In a sensor node, the data-driven processor and its peripheral devices, such as a wireless communication module, consume power. This graph shows that extraordinary power saving is achieved when the prototype uses currently available low-power versions of peripheral devices. To examine whether power saving can be achieved even when the number of sensor nodes is increased, we tried to measure the power consumption of 100 sensor nodes. Since we only have 7 prototypes, we measured the power consumption using a simulator that accurately predicts the power consumption of pipeline stages. This simulation result shows that the entire sensor networking system consumes less than 1/10 of the power consumed by the conventional system.
トリリオンセンサーユニバースを実現するには、稼働し続けられる従来よりも格段に高い信頼性を持つ革新的なセンサーネットワーキングシステムが求められます。具体的には、電池での稼働持続時間が保証されること、さらにはセンサーノードが相互監視によって異常を検知し対処できることが欠かせません。データ駆動プロセッサーは現在のところこれらの要件を満足できる唯一のソリューションです。